A significant part of statistics is testing a claim to see if we can really believe it's true. So that's going to be our question for the day, is how do we test a claim? And today we're going to specifically focus on a claim for a proportion. The process we're going to talk about, though, does work for all sorts of claims. But specifically today, we're going to stay in the context of a proportion. The way we test claims in statistics is what is called hypothesis testing. And the idea behind hypothesis testing is it's this clear process we can do to test if a claim is true. What we'll do is we'll first set up two hypotheses. And they're going to be contradictory hypotheses. Either the first one or the second one is true. The first one we'll call h sub 0. That is what we will call the null hypothesis. And it will always include, it will always use equals. Some variable equals something. And another thing about the null hypothesis is we will always assume the null hypothesis is true until proven otherwise. If the null hypothesis is not true, the other hypothesis is h sub a, which we call the alternate hypothesis. And this is often what we're trying to show to disprove a claim. And this will either use greater than, less than, or not equal to. Kind of the alternative choice. If it's not equal to a number, it must be different than it. And then once we've set up those two hypotheses, we will run a sample or an experiment. And then based on that experiment, we will calculate the probability, the null hypothesis is true based on our sample. This calculation that the null hypothesis is true based on our sample is what we will call the p-value. It's going to be very important to us, the p-value. What is the probability the null hypothesis is true based on our sample? Once we know that probability, we will compare it to the all-important alpha. Alpha, actually no period, we'll just say or the smallest probability that we will still believe the null hypothesis is true. So if our probability, our p-value, is smaller than alpha, that is too small of a probability to still believe the null hypothesis. And so we will have to reject the null hypothesis in favor of the alternative because our p-value was too small. It was smaller than alpha, the smallest probability we still believe the null hypothesis is true. Or the p-value might be bigger than alpha. There is a greater probability that it is actually, the null hypothesis is true, and then we won't reject the null hypothesis. So step 5 is simply either to, make me a little more space, we will either reject the null hypothesis, and we do that if the p-value is less than alpha, because the probability was too small to still believe the null hypothesis. Or we will fail to reject the null hypothesis. And that's the case where the p-value is greater than alpha, or it's just too big of a probability to believe that the null hypothesis is false. A great example to kind of show how hypothesis testing works is to consider a trial. In the United States, we assume in a trial that a person is innocent until proven guilty. And it's actually a perfect statistical hypothesis test. Let's say person A is accused of a crime. The null hypothesis that everyone assumes is true until proven otherwise is that person A is innocent. The alternative hypothesis, what we try and prove or find enough evidence, is that the person is guilty. And what we always do is we assume innocent until proven. That proof is the p-value. What is the probability that they're innocent, given there's all this proof that they are guilty? And not just proof that they're guilty, because you never know for sure they're guilty. We just prove they're guilty beyond a reasonable doubt. And that reasonable doubt, that is the alpha. If you go beyond alpha, if p-value gets smaller than alpha, the proof of innocent is so small, we can no longer assume they're innocent. And there's actually two conclusions that we can make. If proven guilty, if the p-value is so small that they're innocent, the probability they're innocent is so small it's beyond a reasonable doubt, we reject the null hypothesis and conclude the defendant is guilty. If not, at least not beyond a reasonable doubt, we will fail to reject the null hypothesis and conclude, and this is where it gets interesting, and it's very important in statistics, we don't conclude they're innocent. We conclude that they are not guilty. The conclusion focuses on the alternative hypothesis. What's key there is that we never conclude the null hypothesis, h sub 0, is true. We just failed to conclude the alternative. We didn't say they were innocent. We just said there's not enough evidence to say they're guilty. And that's an important conclusion that applies to statistical conclusions as well. We will never conclude the null hypothesis is true. We will always conclude that the alternative hypothesis could not be proven or could be proven. Speaking of conclusions, let's talk about how we want to make our conclusions. Similar to how we interpreted a confidence interval for a proportion, when we make a conclusion, it's really important we make that conclusion in context. But we also are going to focus on the alternative hypothesis, the H sub A. And so a nice script we can follow is we will say there is, or there is not, depending on the context. We will say not if we fail to reject, because we did not get the alternative hypothesis like we wanted. So there is or there is not sufficient evidence to conclude whatever we can conclude. The conclusion, though, is always going to be the alternative, or the alternate hypothesis in context to the problem. Let's do two examples where we can really see what this hypothesis testing thing looks like. Example. First, for doing a hypothesis test specifically with proportions, everything we've done so far actually applies to all hypothesis testing, but specifically with proportions, there's a few formulas we need for proportions. First off, we know that proportions are normally distributed with the proportion acting as the mean and the square root of PQ over N acting as the standard error. But as you calculate these values, different than a confidence interval, because a confidence interval focused on the sample and what we could learn from the sample, we used P and Q from the sample. Here, we're focusing on a null and an alternate hypothesis. So we're going to focus on the claim that the null hypothesis is true. Use the null hypothesis values. And then, to calculate our p-value or our probabilities, we will have z is equal to p hat, the sample proportion, minus p, the hypothesized proportion, divided by the standard error. And remember, the standard error is the square root of PQ over N. So let's try this. Let's say a phone company claims that 43% of smartphone users have an iPhone. But you doubt this claim. So you conduct a survey. Of 83 smartphone users. "44 of them use an iPhone. What can you conclude if alpha equals 0.05? In other words, we're going to believe the claim of 43% until the probability dips below 5% that that claim is actually true. Well, let's set this up. Our null hypothesis has to be that our proportion equals something, and that's the claim that the proportion equals 0.43. For the alternative hypothesis, we can either say the proportion is greater than, less than, or not equal to. There's no direction given in your doubt. When you doubt the 43% is accurate, you're not saying that it's greater or less than. You just doubt that it's accurate. So this is going to actually be not equal to 0.43. And when it's not equal to 0.43, we have what's called a two-tailed test. And what that means is we could reject the null hypothesis if the proportion is bigger or if the proportion is smaller, either direction. Maybe it'd be easier to see if we drew a picture, and we're going to annotate this picture as we go on. Here's the normal curve for the proportion. The claim is that the proportion is 0.43, but we doubt that's true. We think it's either going to be lower, somewhere in the red tail on the left, or higher, somewhere in the red tail on the right. We don't know which side, we just doubt it. It's in both tails, left and right. The distribution, then, of the proportion, just to review, we know that the proportion of our sample will be normally distributed. And again, we're going to use the null hypothesis here. Around the claim of 0.43, with a standard error of 0.43, that's our p, times q, 1 minus 0.43 is 0.57, over my sample size, and here we did a survey of 83 people. So what that really means is our proportion is normally distributed with a mean of 0.43 and a standard error of 0.0543. So, what is our sample proportion? Well, our sample proportion is going to be x divided by n, or the 44 out of 83 people who used the iPhones. And that's going to be 0.53. Run out of colors, so we'll go back to blue. Actually, one thing to put in, since we know our proportion is 0.53, on my picture off to the right, I'm going to put 0.53. That is the x value where the red shading starts. We don't know the value on the left. If our proportion had ended up being less, we would have put the number on the left. But because our proportion was more, we put it on the right. Now we're ready to calculate our z value. And z is our sample proportion minus the hypothesized proportion divided by the standard error. So 0.53, the sample, minus the hypothesized 0.43, divided by the standard error of 0.0543. The z value there is 1.84. So if we have x's on top, we'll stick z's down below. I should have left a little more space. When it's a z, we assume the mean is 0, and our value on the table is 1.84. So let's go to the table and see what area goes with a z value of 1.84. On the table, we're looking at 1.84. So if I scroll over, and if I draw my line straight, we see 1.84 corresponds to an area of 0.4671. But remember, with that area of 0.4671, That is the area in white, 0.4671. We are interested in the area in the tail. To get the tail, we have to subtract from 0.5. That'll give us 0.0329. But what's important to know is because this is a two-tailed test, we have to consider the other tail as well is 0.0329 as well. It's symmetrical, which is nice. So when we want to calculate the p-value, the p-value is the total shaded area. Because this is a two-tailed test, we have to add them together. The 0.0329 plus 0.0329. That gives us a p-value of 0.0658. And remember that p-value is the probability our null hypothesis is true based on our survey. In other words, based on our survey, there is a, change it to a percentage, 6.58% chance the proportion of iPhone users is actually 43%, what the null hypothesis claims. Now, at first glance, you might say that's not a very large percent. But remember, we did say up at the top here that alpha is 0.05. And that means we will continue to believe the null hypothesis is true as long as the probability does not dip below 5%. So if the p-value is 6%, that's not below the 5% threshold, we say that still is not quite enough evidence to kick out the null hypothesis. So our decision is we will fail to reject the null hypothesis, because there's just not quite enough evidence. It was close, but not quite enough evidence to reject the null hypothesis. The reason for that, really clearly stated, is the p-value, the probability the null hypothesis is true, is greater than that alpha, that minimum threshold. Putting the numbers in there, the p-value is 0.0658. That is greater than the alpha of 0.05. So we failed to reject, and we're ready to make our conclusion. Following our script, then, we will say that there is not, because we failed to reject, we'll say not sufficient evidence to conclude. And the conclusion must be in context of the alternative hypothesis. So we're going to state the alternative hypothesis, that the proportion's not 43%. Of course, we must put it in context. So to conclude, the proportion of iPhone users is different than 43%. Now, one thing you might notice is there's a couple of p's going on in here in problems like these, and it's very important we keep them all straight. We have a p-value. That's just the probability the null hypothesis is true. We have a p in the null hypothesis. That is the claim for the population proportion. And we also have a p hat. That is the sample proportion. Be very careful not to get the three p's mixed up. Quite often we'll see students compare the wrong p to alpha, and they'll make the wrong conclusion as a result. Make sure you compare the p-value to alpha to make a conclusion about your p based on your p hat. Sounds confusing, but practice a few to make sure you get them straight. Just to kind of make this interesting, and this isn't always required, but it often is with a hypothesis test, is let's make a 95% confidence interval for the true proportion based on our sample. So based on our sample p hat, our sample we said was 53%, which means q hat, the opposite of that is going to be 1 minus that, or 47%, 0.47. And if we're doing a 95% confidence interval, we should know the z sub alpha over 2, or z sub 0.05 over 2, or z sub 0.025, is equal to 1.96. And we found out in our previous lesson that the error is equal to that z value of 1.96 times the square root of pq over n. But with the confidence interval, notice I will use the sample data. This is different than the hypothesis test where we use the hypothesis. With the confidence interval, we use the sample data of 0.53 times 0.47 divided by the sample size, which was 83. And that will give me an error of 0.107. So my confidence interval then is the proportion 0.53 minus the error of 0.107, and the sample proportion of 0.53 plus the error of 0.107, giving me a confidence interval for the true population proportion to be between 0.423 and 0.637. Or in context, we're saying that we are 95% confident the true population proportion of iPhone users, always put it in context, is between 42.3% and 63.7%. And what you notice is with that confidence interval, our null hypothesis said what we were assuming to be true. The null hypothesis said the proportion was equal to 0.43. Notice that 43% is within that confidence interval. That's why we cannot reject it, because it still is a valid possibility for the true population proportion of iPhone users. I want to do one more example. I know this video is running a little bit longer than normal, but it's really important that we're comfortable with these hypothesis testing. So, it has been claimed that 58.4% of web users prefer Chrome. However, you believe the number is lower. So you're going to test it. You sample 152 web users. And 74 of them use Chrome. With alpha equal to 0.01 this time, we want to be very confident. We're going to go all the way down to a 1% error. What can you conclude? Well, like before, let's start with our hypotheses. The null hypothesis is that the proportion equals what they claim it equals. The claim is that it equals 0.584. The alternative hypothesis is based on what you're trying to show. And this time, we're going to try and show that the actual number is lower, that the proportion is less than 0.584. Which means this time we really have a one-tailed test, or better said, a left-tailed test. Meaning we're going to reject the null hypothesis if we end up far out into the left tail. Drawing a picture, the hypothesized mean is at 0.584. We're going to reject if it's less than, significantly to the left, or in that left tail. So we have our distribution. We know that the proportion is normally distributed at 0.584 with a standard error of, using the null hypothesis, 0.584 times q, which is 0.416, sorry, divided by the sample size of 152, which means it's normally distributed at 0.584, comma 0.0400 when we round. If that's the distribution, then we're going to compare it to the proportion, or the p-hat, that we get from our sample. Our sample said 74 out of 152 use Chrome. 74 out of 152 is 0.487. That's the value off to the left. It's less than 0.487, where the shading starts. Is that far enough away that we can make a conclusion that it's actually less than? Well, to do that, we will go to our z-value, which is equal to our sample proportion of 0.487 minus the hypothesized proportion of 0.584 divided by the standard error of 0.0400. Our z-value is negative 2.43. So we've got our x's on our picture. Putting those all into z's, the mean is 0, and the z-value of negative 2.43 is where the shading starts. Let's go to our z-table. And I got to scroll down a bit to see 2.43. So 2.43. Looks like this time we're going to have a z-value of 0.49. I'm sorry, an area of 0.4925. But that's the area in between of 0.4925. We need the area in the tail, which is just 0.5 minus that, or 0.0075. This time we don't need to worry about the other side because it is a one-tailed test. So my p-value is just that shaded area, the 0.0075. 0.75, which means, based on our survey, there is a 0.75% chance the null hypothesis is true, or the proportion of Chrome users, or people who prefer Chrome, probably would have been a better way to say that, is 58.4%. That is really, really small p-value. In fact, what's really important is when we compare that p-value to our alpha of 0.01. It is actually less than that alpha of 0.01, which means that's too much evidence to the contrary. So we will make a decision to reject the null hypothesis. And the reason for that decision is because the p-value, the probability it's true, is less than the alpha, or specifically 0.0075 is less than the 0.01 minimum threshold. So our conclusion: if we reject the null hypothesis, we will say that there is sufficient evidence to conclude, and then we will state the alternative hypothesis in context, focusing on being less than the 0.584. To conclude, the proportion of web users who prefer Chrome is less than 58.4%. One last little thing as we wrap up our conversation on hypothesis testing is, when all is said and done, we make a conclusion based on a p-value. What's the probability that the null hypothesis is true? Do we reject it? Do we fail to reject it? But when all is said and done, at the end of the day in statistics, we could be wrong. And we really have no way of knowing if we're right or wrong. We can be fairly confident, 95% or 99% confidence, but we could be wrong. And there's two types of errors in statistics that we always try and minimize. We call them type 1 and type 2 errors. A type 1 error is when we reject the null hypothesis when it is true. We should not have rejected it, but we did. The probability of that happening is actually the alpha that we're using in the problem. The other type of error is what's called a type 2 error. And that's where we fail to reject the null hypothesis when we should have, when it is false. And the probability is not as evident for that. We call that probability beta. It comes up in more advanced statistics classes. We're not going to spend a lot of time on that. But you should be aware at this point of what a type 1 and type 2 error is in context. So we did two examples today. The first example was about iPhones. And we failed to reject the null hypothesis. We could have committed a type 2 error, where we conclude not reject, or failed to reject, when we should have. Or to put it in context, and this is probably a better way to say it, or we believe the proportion of iPhone users is 43% because we failed to reject it, but we should have, when it is not. It is not actually 43%. We should have rejected. That's a type 2 error. The second example, because we did reject, could have been a type 1 error, where we conclude reject when we should not have. Or, to put that in context, we currently, after running that sample, we believe the proportion who prefer Chrome is less than 58.4%. Because that's what we concluded. But it's not. That would be a type 1 error, where it's actually either equal to or possibly greater than 58.4%, and we made the wrong conclusion. Those errors hopefully don't happen often to us, but there's always a chance that they could happen, because with hypothesis testing, we're never sure of anything. We could be wrong. And that's what the type 1 and type 2 errors tell us, is what does it mean if we're wrong? So we covered a lot of stuff in this video today. We introduced the concept of what a hypothesis test is and how hypothesis test works. And then we did several hypothesis test examples in the context of proportions. And then really briefly at the end, we talked about we could be wrong, the type 1 and type 2 error. So take a look at the assignment if you want to try a few of these. A little bit of a longer video, but some of the next few are going to be much shorter to make up for it. So we'll see you in class. Now that we've taken a look at how hypothesis testing works, specifically in the context of one proportion, we can extend it to hypothesis testing in many different situations. And one of those situations involves having two proportions, or two groups, and trying to decide, are the two groups the same, or are the two groups different? So our question for the day is, how do we test a claim about two proportions? We're going to have two groups, and we want to know, are these two groups the same? Is one group bigger? Is one group smaller? What can we conclude about these two proportions? And the idea of the hypothesis test is identical to the idea that we did with one proportion. The only difference is we have a few different equations needed to find the test statistic. First thing we need to know is what we're going to call the pooled proportion. The pooled proportion is what the proportion would be if the groups weren't separate. So if we weren't comparing men and women, but we were just looking at people, how many successes are there out of the total group? The pooled proportion we represent with P sub c. the pooled proportion is equal to the sum of the successes from the first group and the sum of the successes from the second group, divided by the number in the first group plus the number in the second group. And as a tip, if you do this on your calculator, you will probably need to put parentheses around the numerator and denominator to make sure that division happens in the correct order, because a proportion should always be between 0 and 1. If your proportion is not between 0 and 1, check the order of operations. So this is our first important formula, finding the pooled proportion in order to test the two proportions, if there was no separation of the groups. The second formula you need to know is the distribution for two proportions. When we compare two proportions, we don't just compare them. What we actually do is we take the first proportion of our sample and subtract the second proportion of the sample. We're actually looking at the distribution of the difference between the proportions. And they are normally distributed, as you might expect. And if they are the same, we should have a difference of 0. The standard error formula is a little bit more involved, but not difficult. It's the pooled proportion times 1 minus the pooled proportion, which might be the pooled Q, times 1 over the first sample size plus 1 over the second sample size. And so that is the second key thing we need, specifically because it is going to help us find the standard error. That big square root is the standard error that we need to calculate the test statistic. With the normal distribution, the test statistic is z. And the test statistic here is going to be the difference in the proportions, p hat a minus p hat b, divided by the standard error. So that's the third new equation we need. Other than that, everything is identical to what we've seen before. So we should be able to jump right in to an example where we will compare two proportions. Let's say a restaurant wants to know if teens are more likely to order dessert than adults. Knowing this information can help them plan their future marketing campaign, so they contact a sample of 84 adults. "33 order dessert. They contact a sample of 91 teens. 46 order dessert. Can they conclude teens are more likely to order dessert if our alpha level equals 0.10. Notice this example is different than when we had one single mean. When we had one single mean, there was a global claim that said the proportion is equal to such and such a percent. Here we don't have any such global claim. Here we're doing a sample of two separate groups And then we're going through and comparing, are these two separate groups different, or are they the same? So setting up our null hypothesis, the null hypothesis is always going to have equality. So the null hypothesis is that the proportion of the teens who order dessert is equal to the proportion of adults who order dessert. Notice I use a subscript on each of the p's so I know which one is which, T for teens and A for adults. That way when I set up my alternative hypothesis, we want to know, are the teens more likely to order dessert? They want to know if the proportion of teens is greater than the proportion of the adults. What we have actually is a right-tailed test because we are going to reject in the right tail. Drawing our little picture. The mean, the assumed difference, the hypothesized difference is that there is 0 difference between them. The order of my hypothesis tells me the order of the subtraction. We always subtract left to right. So what we're really doing is the proportion of teens minus the proportion of the adults. We're claiming the teens are bigger than the adults. So we're taking a big number minus a small number. It should give us a positive number and something in that right tail. That's what we're going to attempt to find. Let's calculate some of the pieces that we're going to need in order to solve this. First, the proportion of teens. There are 46 out of 91 teens that order dessert. That's going to be 0.505. The proportion of adults who order dessert, that's going to be 33 out of 84, or 0.393. And then for our pooled proportion, if there was only one group, not two separate groups, and we just interviewed people, the number of successes would have been 46 plus 33. Over the number of trials would be 91 plus 84. Making sure I use parentheses so I don't get in trouble with order of operations. The pooled proportion is 0.451. We can use that information. Let's not scroll too far. Keep that hypothesis on there. We can use that information to find the distribution. We know the difference in the proportion between the teens and the adults is normally distributed with a mean of 0 and a standard error equal to that big square root. The pooled proportion of 0.451 times 1 minus the 0.451 times 1 over the first sample size of 91 plus 1 over the second sample size of 84, or normally distributed with a mean of 0 and a standard error, if you put that in your calculator, of 0.0752. Now that we know the standard error and the distribution, we can calculate the z-value, the test statistic. Let's label it test statistic. The difference in the proportions, we're going to do the same order as the hypothesis. So we have to do the teens minus the adults. 0.505 minus 0.393 over the standard error of 0.0752. Now, just so I can label it on my picture, let's do the subtraction in the numerator. 0.505 minus 0.393. The actual difference is 0.112 divided by the standard error of 0.0752. So on my picture, the actual difference is 0.112. And when we divide by 0.0752, we get a z-value of 1.49. So if we've got x's in the top row, z's in the bottom row, z's also have a mean of 0, but now the z-value is 1.49. that 1.49 is what we want to look up in the table to find our p-value. Looking at our table then, we have 1.49, so 1.49, that's going to give us an area of 0.4319. So our area of 0.4319, but the p-value is the area in the tail. So we subtract from 0.5 to get 0.0681. So our p-value is 0.0681, which means the probability, or given our sample, I should say, given our sample, the probability the proportion of teens and adults who order dessert is the same is 6.81%. Probability they both order dessert at the same rate is 6.81%. That's what the p-value means. We said we wanted our alpha to be 0.10, which means we will believe the null hypothesis. We will believe the proportions are equal as long as the probability is bigger than 10%. We got a probability of 6%, so our decision is to reject the null hypothesis. And the reason for that decision is our p-value is less than our alpha. There's a 6.81% chance, or let's not do it as a percent, a 0.0681 p-value, which is less than the alpha of 0.10. So we reject the null hypothesis. And we're ready to make our big conclusion. The script for the conclusion remains exactly the same. Because we rejected the null hypothesis, got the alternative we were looking for, we will say there is sufficient evidence to conclude. And then we will go back and state the alternate hypothesis in context, that teens are greater than adults. The proportion of teens who order dessert is greater than the proportion of adults who order dessert. The conclusion is in context. It focuses on the alternative hypothesis. You should feel like what we just did was very, very similar to the hypothesis testing for a single mean. The only difference that we had to do was we had to find this pooled proportion and a new standard error to calculate our test statistic. But the process of the hypothesis test remains the same regardless of what we're testing. So take a look at practicing some of these. We're going to do some of this in class. We'll look forward to seeing you then. Now that we've gotten comfortable with working with the t-distribution and making a confidence interval for a mean, we're ready to do a hypothesis test for a mean. So the question we're going to answer is, how do we conduct a hypothesis test for a mean? And the process of a hypothesis test is always the same, whether we're talking about one proportion or two proportions, or in this case, one mean. The only difference is we have a few different formulas for the mean to help us calculate that important test statistic that will help create the p-value. First off, for the mean, the distribution, because we don't know the population standard deviation, the distribution of the mean is a t-distribution with a subscript for the degrees of freedom, one less than the sample size. The way the standard error is calculated, the standard error is equal to the standard deviation of the sample divided by the square root of n. And then we'll use that standard error to calculate our test statistic. And our test statistic is going to be t equal to the difference between the mean of the sample and the hypothesized mean divided by the standard error. So these are the three pieces that will help us find the p-value to conduct our hypothesis test. Now, because the t-distribution has a slightly different number based on the degrees of freedom, we need a slightly better way than just looking up a value on a table to calculate the p-value and our t's. The way we're going to do that is we're going to use our calculator. First, we have to set up the test. And the way we set up the test is you're going to hit the Stat button. Then you will scroll over to Tests. Then you will scroll down to the t-test. Once you set it up, you have to enter the stats from your study. Now, the calculator has an option of entering the data or entering the stats. We're going to enter the stats. So if needed, select stats. So the calculator knows you're going to actually enter in the stats. And the stats you're going to enter in, first it'll ask for mu sub 0. That is the null hypothesis. It's also going to ask you for x bar, which is the sample mean. It's also going to ask you for what they call SX, which is the sample standard deviation. Then it'll ask you for N, which is the sample size. We know that one. And finally, it'll ask for mu, which is the symbol in the alternate hypothesis, whether that's less than, greater than, or a not equal to. I'll show you how this process looks on the calculator, but it really helps to have an example. So let's do that. Let's build an example. it is claimed the average page in a novel has 275 words per page. To test this claim, you sample 24 pages of a novel. And you find the average page has 260 words. With a standard deviation of 34 words. Do you believe the claim is true if alpha equals 0.05? Well, we start off every hypothesis test with a null hypothesis. Here we're talking about a population mean, and the claim is that the mean is 275 words per page. For the alternative hypothesis, we're not really saying it's less than or greater than. You just want to know, is the claim true? So what we say is mu is not equal to 275. And because we have that not equal, we're really dealing with a two-tailed test. Where we've got our normal distribution. The hypothesized mean of 275 is in the middle, but it actually turned out to be 260, which is less than it. But because this is a two-tailed test, we're going to shade both sides. Those are our x values. We're going to calculate t values off of the distribution. The mean is distributed as a t distribution because we don't know the standard deviation of the population. But we do know the degrees of freedom is 1 less than the sample size. So the degrees of freedom is 23. Let's go to our calculator then to calculate the t value and the p value. Again, that keystroke that we're going to do is first you're going to hit the stat button, which is right next to the arrow. Then we'll scroll over to test. Then we'll scroll down to the t-test. We are going to input the actual statistics, not the individual data values. So we'll highlight statistics. Mu sub 0 is the null hypothesis at 275. X bar is the sample mean. Our sample was 260. Sx is the standard deviation of the sample, which was 34. And n, the sample size, was 24. We're going to make sure we highlight the alternate hypothesis symbol, not equal to, and scroll down to calculate. When we do, you'll see the calculator gives us several things, but what we're interested in most is t and p. T, the test statistic, is negative 2.16, and p, the probability the null hypothesis is true, given our sample, is 0.0413. So let's record that. Our test statistic is t equals negative 2.16. We can add that to our picture to the left of 0. And the p-value is 0.0413. And what that p-value means then, that's the probability the null hypothesis is true. So based on our sample, the probability the average page in a novel having 275 words, that probability is 4.13%. And remember, we said alpha was 5%. 5% is the minimum probability where we will still believe the null hypothesis is true. 4% is less than that, so we can no longer believe the null hypothesis is true. So we will make a decision to reject the null hypothesis. And the reason for that decision is that the p-value is less than the alpha. The p-value is 0.0413, which is less than the alpha of 0.05. That is too little probability. There is overwhelming evidence to reject the null hypothesis. And so we make our conclusion. Following our script, we say that there is sufficient evidence to conclude. And then we state the alternative hypothesis in context. The alternative hypothesis was just not equal to or different than. So there is sufficient evidence to conclude that average number of words per page in a novel is not, or maybe we should say is different, than 475 words. Let's actually take this one step further and build a confidence interval for where we believe the actual mean number of words lies. Let's build a confidence interval. And let's just do a 95% confidence interval. Now, we know the distribution that we're dealing with. We know the degrees of freedom off of that are 1 less than the sample size. The degrees of freedom, we said, was 23 because the sample size is 24 pages. So our degrees of freedom is 23. Alpha, the percent of chance that we're going to be wrong, is 0.05, the opposite of the 95%. So alpha over 2 is 0.025. So we're looking for a t sub 0.025 that has 23 degrees of freedom in our table. Looking at our table, then, we want 23 degrees of freedom. We want 0.025 in a tail. And so that tells us that the critical value we're using this time is 2.069. So t sub 0.025 is 2.069. We're ready to calculate the error that might exist between our sample mean and the actual population mean. Remember, the error is t sub 0.025 times the standard deviation divided by the square root of the sample size. So 2.069 times the standard deviation. We said the standard deviation was 34 words, divided by the square root of the sample size, which was 24. We end up with an error of about 14.4 words. So for our confidence interval, we will subtract and add that error to the mean we got in our sample. Our sample mean was 260. We'll subtract the 14.4 to get a low number. We'll add the 14.4 to get a high number. And so our confidence interval is 245.6 through 274.4. And you notice the hypothesized mean of 275 is outside of that confidence interval, which is related to why we ended up rejecting the null hypothesis. Let's go ahead and interpret it. We can estimate with 95% confidence the population, and we're talking about a mean, and put it in context, number of words per page in a novel is between 245.6 words and 274.4 words. And now we have our confidence interval. So hypothesis testing with a mean, it should feel very similar to hypothesis testing with a proportion, because the process of a hypothesis test is identical regardless of what we're studying. The means are nice because we can use the calculator to make things a little bit shorter and quicker for us, but the philosophy behind the hypothesis test is still exactly the same. So try and take a look at a few of those. We'll look forward to trying a few of these in class and answer any questions that you might have. We'll see you then. The next type of hypothesis test we're going to turn our attention to is a hypothesis test for two means, as we attempt to answer the question, how do we compare two means? And just as is the case with all the other different hypothesis tests, the process is exactly the same. The only difference is we have some formulas to help us set up our test statistic. First, the distribution for comparing two means. When we're comparing two means, we want to know if two separate groups have the same average. Is there a difference between the two groups, or is one group higher or lower than the other group? And when we're interested in comparing them, what we're really comparing is the difference, or the mean of the first group minus the mean of the second group. And because we don't know those population standard deviations, it's going to be a t-distribution with a subscript that represents the degrees of freedom. Now, the degrees of freedom is an ugly formula. If you really want to know what it is, you can look it up in your book. It is in the section in your book preceding the practice assignments that we're doing for today. It's ugly. We are going to cheat, and we will use a calculator. We'll also use a calculator to find the t-statistic, but just so that we have it, the standard error for two means is the square root of the first standard deviation squared divided by the first sample size plus the second standard deviation squared divided by the second sample size. And then we use that standard error to calculate our test statistic, t, which is the difference in the means, a and b, divided by the standard error. But as was the case with the t-distribution with one mean, it will be also the case with the t-distribution with two means that we will use the calculator to do the hard calculations for us. The setup is identical. First, you will hit the Stat button. Then you will scroll over to Tests. And then you will scroll down, but this time you're going to scroll down to select the two sample t-test. Once you're in the two sample t-test, you will enter all the stats we have from our problem. And again, if the calculator is expecting you to enter the data, we're not going to enter the data, so you might need to highlight stats if needed. When you get in there, the first thing it's going to ask you is for x bar 1. That is the first sample mean. Then it will ask you for sx1. That is the first sample standard deviation. And it'll ask you for n1, which is the first sample size. So we enter in all the information about the first group that we're going to compare to the second group, which, as you might expect, you'll see x bar 2, sx2, and n2 is for the second sample that we will compare it with. Then it will give us a mu, which is the alternate hypothesis symbol. We need to tell the calculator, is this a one-tail test or a two-tail test, and which direction it is. And finally, the last thing the calculator will ask us for is if we have pooled data, and for our purposes, the answer is always going to be no. We are not pooling the data. And I'll show you what this looks like on the calculator again, but again, it's going to be easiest to see it if we have an example to work with. So for our example, you want to know if there is a difference in GPA of online students and face-to-face students. So to determine this, you survey 32 online students who have an average GPA of 3.45. With a standard deviation of 0.7. You also interview 41 face-to-face students. Who have an average GPA of 3.67 with a standard deviation of 0.4. If alpha equals 0.10, can you conclude the groups are different? We're comparing the average between the two groups, not just a claim and testing against a claimed GPA. We just want to know, is there a difference between these two groups? We have two means that we're comparing. Well, the mean of the online students is hypothesized then to be the same as the mean of the face-to-face students. Again, I'm using subscripts to make it really clear which group I'm talking about. The null hypothesis, no difference. They are equal. The alternative hypothesis is going to be either one is greater or they're not equal to each other. This example didn't give me any inkling of a direction. They didn't say face-to-face are higher or GPA or online students have a lower GPA or anything like that. So we are just looking to see if the online students are not equal to the face-to-face students, which means we have a two-tailed test. In other words, we have our t-distribution with our hypothesized difference. We hypothesize that the difference between the GPAs is 0, and we'll reject on either tail. Whether it's higher or lower, we will reject on either tail. Well, the actual difference let's add that to our picture. The actual difference in GPAs, and we have to subtract in the same order of the hypothesis. So the online GPA has to come first. The online GPA was 3.45, and we subtract the face-to-face GPA of 3.67, and we end up with 0.22, negative 0.22. So negative 0.22 is the x value we're looking for. We need to figure out what the t values are. Well, our distribution the difference between online students and face-to-face students is a t-distribution, but we don't really know the degrees of freedom because it's got that ugly formula, so we're going to go to our calculator. Again, on the calculator, the way we get to the test is we'll go to Stat. It's right next to the arrows. We'll scroll over to Test, and we'll scroll down to the 2-sample t-test. Make sure Stats is highlighted because that's what we have. Our first group, the online students, we said the online students have an average GPA of 3.45 with a standard deviation of 0.7. And we said that there are 32 of them. The second group, the face-to-face students, have an average GPA of 3.67 and a standard deviation of 0.4, and there were 41 of them. We select an alternate hypothesis of not equals. Pooled is going to be no for our purposes. And when we hit calculate, you'll see the calculator gives us the 3 key pieces of information we need. The degrees of freedom to finish out the distribution. Notice it's an ugly decimal. That's very common with 2 samples. And a t-value and a p-value. Let's copy that information over. So the distribution had 46.5 degrees of freedom. The t-value that came off the calculator was negative 1.59. So negative 1.59 to the left of 0. And a p-value equal to 0.1193. What does that p-value of 0.1193 mean? Well, remember, the p-value is the probability the null hypothesis is true given our survey. So based on our survey, the probability the average GPA is the same for online and face-to-face students is 11.93%. And we compare that p-value to the alpha, which is the smallest probability where we would still believe the null hypothesis is true. We have a greater probability, so we're going to go ahead and say our decision, because the probability, the p-value is bigger than alpha, we will fail to reject. And the reason for that is the p-value is greater than alpha. There's more evidence for the null hypothesis. The p-value is 0.1193, alpha is only 0.10. And so for our conclusion, in context, because we failed to reject, we say there is not sufficient evidence to conclude, and then we will state the alternate hypothesis in context, that there is a difference between the means. There is a difference between the mean GPA of online and face-to-face students. Again, we should start to feel really familiar and comfortable with this process of going through a hypothesis test. It's exactly the same regardless of if we're testing 1 or 2, means or proportions. The process is exactly the same. The only tweak that's different each time is actually calculating the distribution and the test statistic. But we should be very good at the process of setting up and conducting the hypothesis test by now. So you can take a look at those on the assignment. We'll work out with them a little bit more in class, and we'll look forward to seeing you then. Another hypothesis test we can do is hypothesis testing with what are called matched pairs. Matched pairs are where we have before and after data, and we are looking to see, are things the same, or was there some type of improvement? Or maybe we'll pair together couples and see if there's a difference between, the husband's score and the wife's score. Or maybe we'll pair together twins to see if there's any difference between the twins. Or maybe we'll compare your left hand to your right hand. But the data is paired together, and we're looking to see if there's any type of difference. That is matched pairs. And so the question we're going to ask is, how do we hypothesize test for improvement? Or maybe it'd be better to say a difference. Has there been any change? And this is that idea of matched pairs. All the data comes in pairs, and the pairs are matched together. Usually we have that before or after score. And the way matched pairs work is we're going to do a t-test for one mean. Just like we did a t-test for one mean before, the only difference is we will first find the difference for each pair. And then we'll use those differences as our one variable to figure out whether or not there is a positive, negative, or no difference between the before-after data. So with that in mind, we've got some equations that we need to know to run this test. The distribution. It's very similar to the t-test distribution because it is a t-test. The only difference is we're going to put a little subscript of d on the x-bar to represent the average distance is a t-distribution with a subscript representing the degrees of freedom, where the degrees of freedom is simply the sample size minus 1. And then we can calculate the standard error. And the standard error is simply the standard deviation of the differences divided by the square root of the sample size. And we can use that standard error to find our test statistic, which, very similar to the test statistic for a single mean, is t is equal to the difference between the average difference and the hypothesized difference divided by the standard error. And the hypothesized difference is usually 0. We usually assume there's no difference between before and after scores, and we're looking to see, is there a difference, or is it positive or greater than 0, or is it negative or less than 0? Now, like before with the t-test, though, we're going to save all that work with using our calculator to do a lot of the manual crunching of the data for us. So first thing we're going to have to do on our calculator is we're going to have to tell the calculator all of our data. So here's how you enter the data into your calculator. You're going to start by hitting the Stat button. And then you will select Edit to edit a list. And the edit feature will already be highlighted when you hit Stat. So you just really have to hit Enter. And then in L1, you're going to enter the before data, or the first set of data. And then in L2, you will enter the after data, or the second set of data. And then for L3, what you're going to do is you're going to scroll up and highlight L3 and do L2 minus L1, and the calculator will automatically subtract and find all the differences and fill list 3 with the differences. Now the way we get that is you'll hit the second button, and you'll hit the number 2, which will give you L2, minus the second button, and then you'll hit the 1, which will give you the L1. And now in L3, you will have a list of all of the differences between the before and after. A positive difference means it got bigger. A negative difference will mean it got smaller. Then you're ready to actually run the t-test. So you can hit Stat, scroll over to Tests, and then scroll down to t-test. And even though there's 2 sets of data before and after, we're actually just working with the differences. So it's just one t-test. Don't do the 2-sample t-test. It's a single sample t-test. That single sample is the difference between the before and after, checking to see if the numbers went up or down. So when you're running the t-test, you have to enter in some information. First thing you want to do is you want to highlight data, because you have entered the data into the calculator. We don't have the summary statistics. We actually entered the data this time. And that is different than our last t-test. Then you'll see mu sub 0. That is the hypothesized difference. Which is usually 0. We usually hypothesize that there's no difference, or that the difference equals 0. Then it'll ask for the list. The list you want to be L3, where you have all those differences entered. And the way we select L3 is you hit the second, and then the number 3 will give that third list. And finally, we'll enter in mu, which is the alternate hypothesis symbol. Are we looking for it to be smaller after the treatment, bigger after the treatment, or just not equal to 0 after the treatment? And as before, this is a lot easier to see with an example. So let's do an example where we check these matched pairs for some type of improvement. A football coach wants to know if a strength class can help improve his players' bench press weight. The before and after data is below. So we're going to have players. We'll just mark the players with letters to protect their identity, A, B, C, and D. And we'll have weights for before the class and after the class. So before the class, A benched 205. After, A benched 295. That looks pretty good. Before the class, B benched 241. After, B benched 252. Not as dramatic, but still an increase. C benched 338 before the class and 330 after the class. C went down a bit. And D benched 368 and afterwards benched 360. So the question is, if alpha equals 0.05, can the coach conclude the class was helpful? We're going to run a hypothesis test of matched pairs to see if there's a significant difference. First, the null hypothesis is that the average difference is equal to 0. There's no difference. The alternative hypothesis is that the average difference is going to be positive or greater than 0 because the coach wants it to be helpful. He wants the difference to be positive. He wants it to be higher after than before. Which means we have a one-tail test, or better said, a right-tail test. If we were to draw a picture of this, the hypothesized difference is 0. Somewhere over to the right, we hope to see improvement. And we hope that right tail shows there was enough improvement out of the class. Well, our distribution is that the average difference is a t-distribution, and the degrees of freedom is 1 less than the sample size. There are 4 players. 1 less than that is 3. So very small degrees of freedom. It's going to take quite a difference in order to say there's a difference. So from here, let's go to our calculator and see if it can help us find the differences. To enter our information into the calculator, we're going to hit the Stat button right next to the arrows. Edit is already highlighted. If I already had numbers in my list, let's say there were numbers already in here that I didn't want. If you scroll up and highlight the list and hit the Clear button and then Enter, it'll clear out the list, so there's nothing left in the list. The first list is for the before data, so we'll enter in our data 205, 241, 338, and 368. The second list is our after data. Make sure they're entered in the same order, 295, 252, and 330, and 360. Then list 3 is where we're going to put our differences. So if we scroll up to highlight list 3, and then we're going to say take list 2 and subtract list 1. Hit second, and then the number 2, that'll grab list 2, minus second, and then the number 1, and now I see list 3 is equal to 2 minus 1. When I hit enter, I will see all the differences, and that's the data we're going to use in our single mean t-test. To run the t-test, we'll hit Stat, scroll over to Test, scroll down to the t-test, and this time we've actually entered the data into the calculator. So we'll scroll over and highlight the data, enter. The hypothesized mean is 0. For the list, our data is in list 3. That's where the differences are. So we'll hit second and the number 3 to give us list 3. Leave the frequency alone. For the alternate hypothesis, we want to show that the mean is greater than 0. So we need to select the greater than alternate hypothesis. And then we're ready to actually calculate. When we do that, we get our t-value of 0.91 and a p-value of 0.2149. We're also told that the average difference is 21.25. So we can add that to our picture. The average difference is 21.25. But when we convert that to a t-value, the t-value was only 0.91. So the test statistic is that t equals 0.91, which gives us a p-value, an area for that tail of 0.2149. What that p-value means is, given our sample, the probability, the strength class, made no difference in bench press weight, because that's the null hypothesis, is 21.49%. There's a 21.5% chance that the class had no effect on bench press weight. And if we look at our alpha of 0.05, we see that is much bigger than the 0.05 alpha. Alpha is the minimum probability where we still believe the null hypothesis is true. We are well beyond that probability, much higher, so our decision is to fail to reject the null hypothesis. And the reason for that decision is the p-value, the probability that the null hypothesis is true, is greater than alpha, which is our decision break. With numbers, the 0.2149 is greater than the 0.05. And so for our final conclusion, we will state that there is not sufficient evidence. And then we state the alternative hypothesis in context to conclude the strength class increased bench press weights. And so what you see is with the matched pair hypothesis test, it really is exactly the same as a single mean hypothesis test with the t-distribution. The only difference is here we will focus exclusively on the differences. So first we have to calculate that after minus before relationship to see how much things have improved or decreased after the treatment. So that's how we do a hypothesis test for matched pairs. Take a look at a few of these on the assignment, and we will see you in class to continue to work on matched pairs a little more. Quite often we read a claim that a certain population is distributed in a certain way. Maybe we say that 20% fall in one category, 40% fall in another category, and 30% fall in another category. The question we're going to take a look at today is how good that fit actually is to data we might collect. So the official question here, how do we test if data fits a claimed distribution. And as we do this hypothesis test, we have to run into a new distribution that tests how well data fits a claimed distribution. And the new distribution is what we call the chi-squared distribution. And we use the Greek letter chi with a little squared on it. Looks like an X with tails on the ends. And this chi-squared distribution, a few characteristics of it. It is a non-symmetrical distribution. And it is skewed right. So unlike the normal and the t-distribution, which is perfectly symmetrical, the chi-squared is skewed right. In fact, the shape itself varies based on the degrees of freedom. There is a different shape based on the degrees of freedom. And another unique thing about the chi-squared is that it is always greater than 0. With the t-distribution and the normal distribution, we found it symmetrical around 0. We had positive values and negative values, representing if we were left or right of the mean. The chi-squared doesn't do that. The chi-squared actually starts at 0, and depending on the degrees of freedom, if there's only 1 degree of freedom, the graph looks something like this. But if we increase the degrees of freedom to maybe 3, it's going to look something like this, with a little hump skewed to the right. And the more we increase the degrees of freedom, that hump is going to move slightly over. So this red line might represent 10 degrees of freedom. And so you see the shape varies quite dramatically based on the number of degrees of freedom we have. So let's look at how we can use the chi-squared distribution to test a claimed distribution. What we're going to do is the goodness of fit test. Or we've got some claim that a certain percent fall in various categories. Is that claim accurate? Does the data fit that distribution well? Is it a good distribution? The test statistic we will use is chi-squared is equal to the sum of the observed frequency minus the expected frequency squared divided by the expected frequency. So we've got some new variables. O is the observed frequency, and E is the expected frequency. And this chi-squared value we're going to calculate by hand. It's not too bad, but it is one we should know how to do. Now, with chi-squared, we have to know the degrees of freedom. The degrees of freedom with the goodness of fit is 1 less than the number of categories. And then for our null hypothesis and alternative hypothesis, with the goodness of fit test, we usually state it in a sentence rather than symbolically, like we did with the means in the t-distribution or the normal distribution. So in words, the null hypothesis is that the data fits the distribution. The alternate hypothesis is that it's not equal to the distribution, or that the data does not fit the distribution. And what's interesting about the chi-squared, because it starts at 0 and is skewed right, that alternate hypothesis is always going to be a right-tailed test. In fact, with chi-squared, almost always we're working with a right-tailed test. There's only one context, which we'll talk about in another video, where we could have a two-tailed test or a left-tailed test. But in general, chi-squared is a right-tailed test. Now, we can use our calculator to help us find the area that's in that right tail. So let's take a look at how the calculator can do that. What we'll do on the calculator is we will find the area from the test statistic all the way out to infinity. How much area is in that right tail? The problem is our calculators can't do infinity. So we're going to put a number in that's pretty darn close to infinity. We're going to use 10 to the 99th power to represent infinity, because there's going to be very little area that's past 10 to the 99th power. That's a 1 with 99 zeros after it, a 100-digit number. That's pretty darn close to infinity. So the calculator keystrokes we want to do is, first you'll hit the second button. Then you'll select the distribution function, which is really the vars button. And then above it, with the second feature, you're getting distribution. Then you can scroll down to the chi-squared CDF. Once you've selected the chi-squared CDF, what you'll do is you'll enter the test statistic to represent the minimum value we're finding the area of. Then you'll do a comma. Then you will do the infinity, which is 10 raised to the 99th power. Then you will do a comma, and then you'll type in the degrees of freedom. We'll see this process work out when we do our example now. Let's say a researcher wants to verify a claim about her community. She wants to verify the claim about her community that 40% of the residents speak Spanish in the home. %, speak Russian. 45% speak English. And 5% speak other languages. So the researcher does a survey. In a survey of 200 community members, 71 speak Spanish. 23 speak Russian. 102 speak English. And 4 speak another language. If alpha equals 0.05, can the researcher conclude the claimed distribution is accurate? We're going to go through the same process of a hypothesis test that we've gone through before. We've just got a different test statistic, but everything's exactly the same from there. Our null hypothesis, we said, is that the language, put it in context, but that the claim is accurate, that the language spoken in the home matches the distribution of the claim. The alternative hypothesis is that it does not match the claim, that the language spoken in the home does not match the claim, or the distribution of the claim. I should say distribution because that's important. And we said with the chi-squared, we are almost always dealing with a right-tailed test. We end up more in the right tail, the more different we are from the distribution. The distribution itself is a chi-squared distribution, and we'll do a little subscript for the number of degrees of freedom. We've got Spanish, Russian, English, and other. 4 languages. The degrees of freedom is always 1 less than the number of categories. So we have 3 degrees of freedom. And now we're ready to calculate the test statistic. And this is where we're going to do our real work. We've got Spanish, Russian, English, and other. The claimed proportion, can't get it all on one page here, but we've got 40% with Spanish, 10% with Russian. So Spanish is 0.4, Russian's 0.1, English 45%, 0.45, others 5%, 0.05. The expected value we've done a survey of 200 community members. So of those 200, we should expect 40% to speak Spanish. So we can calculate 40% or 0.4 times 200, and that gives us, we would expect 80 people in our survey to speak Spanish. For the Russian, we'd expect it to be 10%. 10% of the 200, 0.10 times 200 is 20. For the English, 0.45 times 200 is 90. And for the other, 0.05 times 200 is 10. So we use those percentages and the total sample size to calculate what we expect to happen. But something different happened in our observed probabilities. What we observed is 71 spoke Spanish. This is from our survey. We observed 23 Russians. We observed 102 English. And we observed 4 other languages. So now what we can do is we can use that chi-squared statistic is the observed minus the expected squared divided by the expected. Similar to how we did the standard deviation by hand back in chapter 1, we're going to just make a different column so that we can sum those observed minus expected squareds over expected. So first, observed minus expected. Observed minus expected. The observed comes first. So 71 minus 80 is negative 9. 23 minus 20 is negative 3. 102 minus 90 is 12. Oops, I'm sorry. 23 minus 20 is a positive 3. And 4 minus 10 is negative 6. Then we square those values. The observed minus expected squared. 9 squared is 81. 3 squared is 9. 12 squared is 144. And negative 6 squared is 36. Now we take the observed minus the expected squared, and we divide by the expected value. The expected value column is that second column here. So 81 divided by 80 is 1.0125. 9 divided by 20 is 0.45. 144 divided by 90 is 1.6. And 36 divided by 10 is 3.6. Now we're ready to actually find that sum of the observed minus expected squared divided by the expected by adding up that last column. 1.0125 plus 0.45 plus 1.6 plus 3.6 gives us 6.6625. That is our chi-squared test statistic. Now that we have our test statistic, we are ready to calculate a p-value. And we're going to do that p-value by doing the chi-squared CDF. We're going to go from a low value of 6.6625 to a high value of infinity, which we use 10 to the 99th power for infinity. And we said we had 3 degrees of freedom. So on our calculator, to get the chi-squared distribution, we're going to hit second, and then the vars button, which gives us distribution. And we'll scroll down. We want the chi-squared CDF. It has to be the CDF. Make sure you don't do the PDF. We're never going to use that one. The CDF, the lower limit is 6.6625. The upper limit is infinity, which we'll use 10 to the 99th power. And the degrees of freedom is 3. And when I hit paste, you see it types those numbers in for me. If you don't have the newest model of the TI-84, you might just have to enter in these numbers with commas separating them. Get the same thing, though. We end up with 0.0835. 0.0835. And what that p-value tells us is the probability that null hypothesis is true given our data. Based on the survey, there is an 8.35% chance the proportion of people who speak various languages matches the claimed distribution. %8 chance that it matches the claimed distribution, but we said that alpha is 0.05. In other words, we will believe the claimed distribution all the way down to 5%. We only have an 8%, or we still have an 8%, so we're still going to believe that null hypothesis. Our decision is to fail to reject the null hypothesis. And the reason for that decision is because our p-value is bigger than alpha. There's enough evidence to still believe the null hypothesis. Specifically, the p-value was 0.0835, which is bigger than alpha, which was 0.05. So we can make a conclusion in context, focusing on the alternative hypothesis. We say that there is not sufficient evidence to conclude the distribution of languages spoken in the home is different than the claimed distribution. Not enough evidence to say it's different, so we'll have to be stuck believing that distribution is true. That's the goodness of fit tests. The hypothesis test process still exactly identical. We just have a new distribution of chi-squared. We have to do a little bit of arithmetic to calculate that chi-squared value, but it's not too bad. So go ahead and take a look at a few if you want to practice some. We'll talk about it more in class. We will see you then. Another use for the chi-squared distribution is testing to see if two variables are dependent or independent of each other. So the question for today is, how do we test if two variables are dependent or independent? And to do this, we will test for independence. What we'll do to test for independence is we will collect frequency data and organize in rows and columns. For example, we might compare gender to we'll just do male, female, to whether or not you played sports in high school, yes or no. And this will generate a table where we'll enter in how many yeses, how many nos for each gender. We'll probably also have a column for totals and a row for totals. And then off this contingency table, we will see if playing sports is dependent or independent on gender. Once we have our frequency information, we also need to calculate the expected frequencies. And often I'll make a second table to do this of expected frequencies. And the way we calculate the expected frequency is we will take the row total times the column total divided by the total of the entire survey. And we'll have to do that for every single cell. So first row, first column, first row, second column, second row. Find all the entries for their expected frequencies. And then we can calculate the test statistic from here. Often I'll organize this in a third table, because our chi-squared is going to be equal to the observed value minus the expected value squared divided by the expected values, and then we take the sum of all of those. So we've got two equations that are going to be helpful to test for independence. You should know how to calculate the expected values, and then from that calculated the chi-squared. Now, as we're testing for independence, we need to know the degrees of freedom. The degrees of freedom is equal to a product with independence. It's the product of the number of rows minus 1 times the number of columns minus 1. Also with independence, similar to when we did goodness of fit, the null hypothesis and the alternative hypothesis are generally in words, not in symbols. So the null hypothesis is generally going to be that the variables are independent. And then the alternate hypothesis is that they're not independent or that they are dependent. And then similar to the goodness of fit test, that dependence is always a right-tailed test. So let's try an example and see if we can test for independence. An example. A restaurant wants to know if breakfast preference is dependent on gender. So the following data is collected. And they're going to compare male to female. And some are going to prefer French toast. Some will prefer pancakes. Some prefer waffles. And some prefer omelets. And then we'll have a total row and a total column. We find 47 males prefer French toast, 35 prefer pancakes, 28 prefer waffles, and 53 prefer omelets. If we add all of those together, we'll get a total of 163 males were surveyed. For the females, 65 prefer French toast, 59 prefer pancakes, 55 prefer waffles, 60 prefer omelets. We interviewed a total of 239 females. And if we total the individual breakfast choices, we've got 112 who prefer French toast, 94 who prefer pancakes, 83 who prefer waffles, and 113 who prefer omelets. There's a total of 402 individuals in this survey. The question is, if alpha equals 0.05, can the restaurant conclude that breakfast preference is dependent on gender? Well, let's set up our hypothesis test. First, we have our null hypothesis, which states that breakfast preference is independent of gender. Breakfast preference does not change based on if you're male or female. The alternative hypothesis is that there is some type of dependence, that breakfast preference is dependent of gender, or on gender. As usual with the chi-squared, we have a right-tailed test. And our degrees of freedom to help us calculate the actual distribution is going to be the number of rows. We've got 2 rows. Don't count the total. 2 rows minus 1 times the column. Don't count the total again. 1, 2, 3, 4 columns minus 1. Which gives us 1 times 3, or 3 degrees of freedom. Our distribution for our chi-squared statistic is a chi-squared with 3 degrees of freedom. Then let's see if we can calculate our test statistic. To calculate the test statistic, we first need to make another table of our expected values. So for our expected values, we'll do the same table, male and female. And for French toast, I'll give it a little more space here. The way we calculate the expected value for our males with French toast is we will take the row of males and the column of French toast, those totals. So the row of males had a total of 163. The column had a total of 112. That's how we get the French toast male cell for expected. 163 times 112, and then we'll divide by the total. So we have 163 times the 112 divided by the total number of people, which was 402. The expected value for French toast is 45.41. Now we'll go over to pancakes. Pancakes is in the second column, first row. So in this case, what we'll see is we want the pancakes for the males. That's in the first row, second column. So those are the numbers we're going to multiply 163 times 94 and divide by the 402. The row times the column. So we have 163 times 94 divided by the total of 402. We end up with 38.11 is the expected value for pancakes. Next is waffles. With the waffles, we want the third column in the first row. So we're going to multiply 163 times 82 and divide by the total. So we have 163 times the 83. Is it 83? Yeah. Divided by the total of 402. And that's going to give us 33.65 for our expected value. Finally, we've got the omelets. Similarly with the omelets, the total for the omelet row for the males was 163. The total number of omelets was 113. And then we divide by the 402 to get 45.82. We'll do the same thing with the females. This time the female row total was 239. So we're going to do 239 times the French toast total of 112 divided by the 402. The expected females who prefer French toast should be 66.59. With the pancakes, 239 times the column total of 94 divided by the total of 402, 55.89. With the waffles, the row total of 239 times the column total of 83 divided by the total of 402. The expected value is 49.35. And finally, with the omelets, the row total is 239. The column total 113 divided by the total of 402. The expected number of omelets for females is 67.18. So we've got this second table that demonstrates for us all of the expected values based on the row totals and the column totals. Next, I'll make another table that does the observed minus the expected squared divided by the expected. For our males, females. First with the French toast. Our first cell, and I've got to do a lot of scrolling here. Hopefully you can see it all on one screen. 47 is what we observed. 45, actually I'll go ahead and highlight it to emphasize what I'm looking at here. Highlighted in yellow here, our first cell had an observed value of 47, an expected value of 45.41. So plugging that into our formula, the observed value of 47 minus the expected value of 45.41 squared divided by the expected value of 45.41, that equals 0.06. Then we'll do the pancake preference. You'll see pancakes, the observed value is 35. The expected value is 38.11. So we plug it into our formula. 35 minus 38.11 squared divided by the expected value of 38.11, that gives us 0.25. Waffles. Same thing. We'll come up here. We observed 28 waffles. We expected 33.65. So we plug that into our formula. 28 minus 33.65 squared divided by the expected value of 33.65, we get 0.95. And we'll keep going with all of our remaining cells. For the omelets, we observed 53. We expected 45.82 squared divided by the expected 45.82. That equals 1.13. Doing the female row, the observed French toast was 65 minus the expected 66.59 squared divided by the expected 66.59 equals 0.04. With the pancakes, the observed value of 59 minus 55.89 squared divided by the 55.89, that equals 0.17. For the waffles, the observed value was 55 minus the expected value of 49.35 squared divided by 49.35 equals 0.65. And finally, the observed value for the omelets was 60 minus 67.18 squared divided by 67.18. That's going to give us 0.77. So we're going to get really good at that observed minus expected squared formula. And the reason we need to do that is our chi-squared test statistic is going to equal the sum of those observed minus expected squared divided by the expecteds. We're going to actually add all 8 of these numbers that we just found together. And when we add all those numbers together, you should get 4.02. That is our test statistic. So it's a little cumbersome and tedious to calculate because you've got to go through cell by cell. First, we calculate the expected values by taking the row total times the column total divided by the total. Then you need to find that observed minus expected squared divided by expected. Plugging those values in, calculating them out, and then finally we add them together to get our final chi-squared value. And now we're ready to go on with our hypothesis test. Everything should flow pretty quick from here. We need to calculate a p-value, or the probability the null hypothesis is true. To do that, we'll do the chi-squared on the calculator CDF. the minimum value of 4.02, all the way to a maximum value of infinity, 10 to the 99, and we said there are 3 degrees of freedom. So let's do that. We'll hit second. The distribution, or vars button. We'll scroll down to select chi-squared CDF. The lower value we want is 4.02. The upper value is infinity. 3 degrees of freedom. Again, if you don't have the newer software, you just have to separate them by commas. And when we hit enter, we find a probability of 0.2593. 0.2593. Which means there is a 25.93, actually let's say based on our survey. Based on our survey, there is a 25.93% chance that breakfast preference is independent of gender. And we said we would believe the null hypothesis that they are actually independent as long as that probability does not go below alpha of 5%. 25% is well above that. And so we will make a decision to fail to reject the null hypothesis. And the reason for that decision is the p-value is greater than alpha, or 0.2593. That's too much evidence, overwhelming past the 0.05. We must still believe the null hypothesis is true. So we make a conclusion. Our conclusion is that there is not, always in context in the alternative hypothesis, there is not sufficient evidence to conclude breakfast preference is dependent on gender. And that is how we do a chi-squared test for independence. It takes a little bit of time to calculate the test statistic running through those calculations, but it's not too difficult. It just takes the time to run it out. So go ahead and take a look at trying a few of these. Off the homework, we'll do a few of these more in class as we look at it a bit further. We'll see you then. Today we're going to take a look at another use of the chi-squared distribution, and that is testing a claim about a single variance. Our question's going to be, how do we test a claim about a variance? And when we're testing a variance, a single variance, we have a test statistic, which is a chi-squared statistic. The formula with a variance for chi-squared is the sample size minus 1 times the sample variance divided by the divided by the population variance. And we need to be very careful or be very aware of what we have in the problem. We use sigma and s to represent the standard deviation. But when those pieces are squared, and we either have sigma squared and s squared, those represent what we call the variance. And so the formula says s squared and sigma squared, those values represent the variance if it's already been squared. If it hasn't been squared, we would have sigma and s, the standard deviations, which need to be squared in order to find the test statistics. So we need to be very careful. Do we have s or s squared? Do we have sigma or sigma squared, and not get those backwards? Also, with chi-squared, we need to know the number of degrees of freedom we have. The degrees of freedom are always 1 less than the sample size with the chi-squared. And something that's unique about testing a variance is that it can be either left, right, or two-tailed test. And this is very unique because normally with the chi-squared, we're dealing with a right-tailed test. But in the context of the variance, it's the only time we're allowed to have either a left-tailed test or a two-tailed test, which doesn't happen as often. So the best way to really attack this is to run through an example. So let's say a customer wants to know how the cost of a list of school supplies varies from store to store. A teacher claims the standard deviation is only $15. So to test this, the customer surveys 43 stores and finds a mean of $84 and a standard deviation of $12. Test if the standard deviation is less than the teacher's claim of $15. If alpha equals 0.05. So we've got a claim about the standard deviation. The claim is that the standard deviation is $15. But notice that's the standard deviation, not the variance. The variance is the standard deviation squared. So when we set up our null hypothesis, our null hypothesis will state that the variance, or sigma squared, is equal to the standard deviation squared, or 15 squared, which is 225. Notice again, we had to square the standard deviation to get the variance. The alternate hypothesis, we believe that the variance is actually less than 15 squared, or less than 225. Because we're interested in less than, we actually have a left-tailed test. So let's draw a little picture of our left-tailed test. Chi-squared is skewed right. And we're interested in being in the left tail. Now, in the survey, the standard deviation ended up being 12 compared to the actual mean of 15. Is that enough to reject the null hypothesis? Well, first we need to know the degrees of freedom. The sample size, minus 1. 43 minus 1, we've got 42 degrees of freedom. And then we'll also calculate the test statistic. The test statistic is chi-squared is equal to n minus 1, 42 minus 1, times s squared. S, I'll go ahead and actually write the formula here one more time so we can see it. N minus 1 times s squared divided by sigma squared. S is the standard deviation of the sample. So for my sample, the customer did a survey and found a standard deviation of 12. That is my sample standard deviation, 12 squared to get the variance, divided by sigma, the claimed distribution of the population. The claimed standard deviation is 15. So we'll divide by 15 squared. And when I do this on my calculator, oops, sorry, the sample size was 43. 43 minus 1 times 12 squared divided by 15 squared, we get a test statistic of 26.88. Now that we have a test statistic, we're ready to find the p-value, or the probability my null hypothesis is true. The probability the standard deviation is actually 15. It's a chi-squared CDF. Normally with chi-squared, we go from smallest to largest. Here, the smallest value on the chi-squared is going to be 0 to the largest value of 26.88, comma, our degrees of freedom, we said was 42. And let's see what the calculator gives us for that value. To get the chi-squared distribution, we'll hit second, vars, so we get the distribution. We'll scroll down to chi-squared CDF, going from 0 to 26.88. Our degrees of freedom are 42. And we'll hit paste. If you have the older version of the software, you just enter those numbers in separated by commas, like you see on the screen here. And when we hit enter, we find a probability of 0.0337. 0.0337. That p-value tells us that based on our sample, the probability that the null hypothesis is true, that the standard deviation of the cost of school supplies being 15 is 3.37%. There's a 3% chance that that null hypothesis is true. Well, if that's the case, we're ready to make a decision. The decision point is always compared to the alpha. And we said alpha was going to be 0.05. 5% probability we'll still believe the null hypothesis. We only have a 3% probability, so we can no longer believe the null hypothesis. So we will reject the null hypothesis. And the reason for that decision is that the p-value is less than the alpha value, or that 0.0337 is less than the 0.05. And so our conclusion, which focuses on the alternative hypothesis in context, we can say that there is sufficient evidence to conclude the standard deviation of school supplies cost is less than $15. And that's all there is to testing a single variance. It's actually the easiest chi-squared problem to solve because it's very straightforward. We don't have to find all those expected values that we do in other chi-squared tests. So we test a single variance with our new chi-squared test statistic. And then we run it through the same process of a hypothesis test that we've been seeing for several weeks now. We should be very good at setting up these hypothesis tests. So you can go ahead and take a look at a few of these on your homework assignment. We'll look at this more in detail in class, and we will see you then. Now that we've taken a look at how a hypothesis test can be conducted for a claim about a single variance, we can extend this to the next level and look at a hypothesis test on a claim of two variances. And so the question we're going to answer is, how do we compare two variances? And similar to one variance, we have to be careful if we're talking about standard deviation or variance, because the standard deviation is the square root of the variance. But different than the single variance is we need to introduce a new distribution that models a comparison of two variances. And this new distribution is what we will call the F distribution. The F distribution, because this distribution is used as a fraction when comparing two variances. Similar to the chi-squared distribution, the F distribution is not symmetrical. In fact, it is also skewed right. Also, similar to the chi-squared, is its shape is different based, I should say different shape, based on degrees of freedom. But what's really unique about the F distribution is it's a fraction of two variances. In other words, we're going to have a ratio, or let's just go ahead and call it a fraction, or a ratio, with two sets of degrees of freedom. We say the numerator has degrees of freedom for the numerator is equal to the first sample size minus 1. And the denominator is going to be the degrees of freedom of the denominator is equal to the second sample size minus 1. And what's interesting is as the degrees of freedom get larger for both the denominator and the numerator, the curve becomes more normal. One last thing to talk about the F distribution is similar to the chi-squared. The F is always positive, or always greater than, I guess it could be equal to 0. So that's kind of a brief introduction of the F distribution. We're going to use our calculator to do most of the calculations with the F distribution. What we're interested in is, can we set up and carry out a hypothesis test on 2 variances? The test statistic for 2 variances is simply the fraction, the first variance divided by the second variance, or the standard deviation squared divided by the standard deviation squared. If both variances are equal, if we have equal variances, that tells us that F is going to equal to 1. We're dividing everything by itself. If we have different variances, F is closer to 0 if the second variance is larger, or infinity if the first variance is larger. We'll use our calculator actually to do most of the work for the F statistic. And so just really briefly how to do that. First, you're going to hit the Stat button. And then you can scroll over to Tests. Then you can scroll down to 2SAMP F test. And that's where we can access the 2-sample F test for the comparing of our variances. Then to actually enter in our data, you want to make sure that stats is highlighted. And then you can enter the standard deviation. Notice I did not say the variance. Even though we're comparing variances with the F test, the calculator wants us to enter in the standard deviation, which is the square root of the variance. So we can enter the standard deviation and our other data. Other than that, the hypothesis test is going to work exactly like all the other hypothesis tests we've seen before. So let's try an example and see if we can do a test of 2 variances. Quality control is interested in the variance of 2 machines making widgets. The first make 32 widgets. With a variance in the radius Apparently there's a circle on these widgets. Of 4.1 millimeters. The second makes 37 widgets with a variance in the radius of 3.7 millimeters. At the alpha equals 0.05 level, can quality control conclude the first machine has a higher variance? We'll start by setting up our null and alternative hypothesis, like always. The null hypothesis always has equity, so we're assuming with our null hypothesis that the variance of the first machine is equal to the variance of the second machine. The alternative hypothesis is that the variance of the first machine is greater, because we want the first machine to be higher than the variance of the second machine. For our degrees of freedom, the degrees of freedom of the numerator, we always do our division in order as listed in the hypothesis test. So we're going to do the variance, the variance of the first machine divided by the variance of the second machine. Same order as they're in the hypothesis test. So the first machine is our numerator. The first machine made 32 widgets, meaning the degrees of freedom of the numerator are 31. The degrees of freedom in the denominator being the second machine, which made 37 widgets, one less would be 36 for the degrees of freedom. So our distribution is that we have an F statistic that is distributed as an F with 31 and 36 degrees of freedom. And we can calculate our test statistic by just dividing those variances. Notice we're given the variances. The variance is 4.1 and the variance is 3.7. They've already been squared. So the first variance is 4.1. divided by the second variance of 3.7. That gives us 1.1081. So if we were to draw a picture of this situation, the F distribution skewed right, we have a test statistic right at 1.0181. We want to be greater, so we go for the right tail. How much area is in that right tail? This is where we're going to go to our calculator to find our p-value. First, we're going to hit Stat, scroll over to Test, and then we're going to scroll down for the 2-sample f-test. There it is, 2-sample f-test. I'm going to enter in the statistics. And it wants my first standard deviation, not the variance. The calculator's asking for the standard deviation, which is the square root of the variance. Fortunately, I can just type in the square root with the second, and then the square root key is above the square, diagonal from the 7. And my first variance was 4.1. So if the variance is 4.1, the standard deviation is the square root of 4.1. And when I hit enter, it's going to calculate that value for me. The first sample size had 32 widgets in it. The second machine had a variance of 3.7. So we'll take the square root of 3.7 to get the standard deviation of 1.92. And the second machine made 37 widgets. For our alternate hypothesis, we said that the first is greater than the second, so we'll select greater than. And go down and hit calculate. Notice it gives us the exact same F statistic that we found, 1.1081. But what we're really interested in is it gives us a p-value of 0.309. 3809. So let me scroll a bit. Give me a little more space to work. We have a p-value of 0.3809. Remember, the p-value is the probability the null hypothesis is true. So we will say the probability, or based on our sample, the probability both machines have the same variance, that's the null hypothesis, that they're equal, is 38.09%. And the alpha tells us the probability required to disprove that null hypothesis. We have to drop below 5%. We're well above the 5%, so we're ready to make a decision, which is to fail to reject the null hypothesis. And the reason for that decision is that the p-value is greater than alpha. There's too much evidence in support of the null hypothesis. Specifically with numbers, 0.3809 is greater than 0.05. And so for our final conclusion, which is always written in the context of the alternative hypothesis, I'll leave the alternative on there, is that there is insufficient, or there is not sufficient evidence to conclude the first machine has a higher variance than the second machine. And that is how we can compare two variances. So we have a new distribution, the F distribution, which is a fraction of the variances. But the idea is still the same as our hypothesis test we've been doing. We've got our null and alternative hypothesis. The test statistic gives us an area, a p-value that we compare to alpha and make a conclusion whether or not we have sufficient evidence to believe the alternative hypothesis. Take a look at a few of these on your own if you'd like. We'll talk about comparing two variances more in class, and I'll look forward to seeing you then. Quite often in statistics, we're concerned with comparing the mean from more than just two groups. In the past, we compared two groups with the t-test. But here, when we compare more than two groups, we need a different statistical test. And that's what we're going to look at today. How do we compare the means of more than two groups? This actually also works with two groups, but the t-test is easier. The t-test turns out to be a special case of this thing that is called the ANOVA. But the t-test is easier for two groups, so we do the t-test. But when there's more than two groups, we use this test called the ANOVA. ANOVA is actually an acronym. It stands for Analysis of Variance. And the idea behind the ANOVA is we compare the variance between the groups to the variance within the groups. And when we divide them, we end up with an F statistic. And so we can compare using the F ratio, just like we did with two variances. So a couple differences with the ANOVA, the hypothesis test. For the hypothesis, the null hypothesis is always the same, that the first mean is equal to the second mean, which is equal to the third mean, which is equal to all the other means until you get to the very last mean. Basically, all the means are the same. And the alternative hypothesis is that at least one mean is different. We don't know which mean, but just one mean is different than the rest. Possibly all three are different from each other. And we use the F test to compare which hypothesis we'll end up going with. What we're doing is we are looking for a difference, but not where the difference is. Turns out that once we decide that there actually is a difference between one of the means, we have to do some follow-up statistical tests, which are beyond the scope of this course, to identify specifically where that difference is. We might have an idea where it is, but to get the exact difference, we need follow-up tests that we're not going to cover in this course. So for today, all we're looking at is, are they all the same, or is there a difference somewhere? We're not going to spend our time in this course with the complex calculations of the ANOVA. We're just going to look at actually carrying it out and having our calculator do the complex calculations. How we're going to do this is we're going to put each group in its own list. And the way we do that is we'll hit the Stat button, and then we'll select Edit to edit our list. And in list 1, we'll put the first group data. List 2, we'll put the second group data. List 3, the third group data, until we get all of our groups. And once all of our groups are actually listed in there, we will run the test. And we'll do that with the Stat button. We will scroll over to Tests. And then we will scroll down to the ANOVA. Now, the ANOVA will not give us prompts on what information to enter in like a lot of the other statistical tests did. So what we need to do is we're going to enter the lists separated by commas. And the way we get the list is we'll hit second and then select the list number. And we'll see how that all works out with our example. Let's go ahead and move to our example and see if we can compare this time, this context, we're going to compare 3 groups and see if they have the same mean or different means. A university is comparing traditional students, transfer students, and non-traditional students. By comparing GPA in the junior year, here are their results. The traditional students had GPAs of 3.2, 3.4, 3.7, 4.0. The transfer students had GPAs of 3.1, 2.7, 2.9, 3.2, and 4.0. And the non-traditional students had GPAs of 3.4, 2.2, 2.7, and 2.8. We want to know if all three groups can be considered to have the same GPA or different GPAs. If alpha equals 0.10, can the university conclude there is a difference in the groups? Let's scroll up and give ourselves a little room and start our hypothesis test. The null hypothesis is that the mean of the traditional students is equal to the mean of the transfer students, which is equal to the mean of the non-traditional students, that they all have the same mean. The alternate hypothesis is that at least, possibly more, one group have a different GPA. Let's go ahead and run this test on our calculator and see what happens. First thing we need to do on the calculator is enter our data into stats, and we'll select edit. If there's extra stuff in this list, you can highlight and hit clear enter, and that'll delete the list, or clear the list. Clear enter. Clear enter. And so in list 1, I'm going to put the GPAs 3.2, 3.4, 3.7, and 4.0. List 2 is my second group, 3.1, 2.7, 2.9, 3.2, and 4.0. The non-traditional group, 3.4, 2.2, 2.7, and 2.8. Now let's go ahead and run the ANOVA. We'll hit Stat, and this time going over to Test, and all the way down to the bottom, or hitting up gets us straight to the bottom, you'll see ANOVA. For the ANOVA, we enter in our list. We had the 3 list, so second, 1 for the first list, comma, second, 2 for the second list, comma, second, 3. And we'd keep going based on how many lists we have. We only had 3 lists. And when we hit enter, we get all sorts of information. We've got our F statistic of 3.07. We've got our p-value of 0.09. Under factor, you'll see we've got degrees of freedom equals 2. And under error, we've got degrees of freedom equals 10. The other numbers we're not going to concern ourselves with today. But those degrees of freedom represent the numerator and the denominator. So the factor is the numerator 2, the Error is the denominator 10. They are in order, which is nice. So when we say our distribution, we'll say f is distributed as an f statistic with 2 and 10 degrees of freedom. And we just found out that f equals 3.07. And more specifically, our p-value, that's the important one, was 0.0912. I'm going to also go ahead and draw a picture of what's happening. There's my f distribution, my test statistic at 3.07, and we shade that tail, which we now know has an area of 0.0912. Now, speaking of the p-value, what that p-value means is based on our sample, the probability all three groups of students have the same mean GPA in the junior year is 9.12%. We've got a 9% chance that all three groups have the exact same probability. The p-value is the probability the null hypothesis is true, which means we are ready to make a decision. The decision is based on the alpha. We said alpha is 0.10. We're going to believe the null hypothesis is true until there's less than 10% chance it actually is true. We have a 9% chance that it's true, so that passes our threshold, so we will reject the null hypothesis. And the reason for that decision is that the p-value is less than the alpha, or the 0.0912 is less than the 0.10 we said was our decision breakpoint. So our conclusion, in context of the alternative hypothesis, is that there is sufficient evidence, because we rejected, to conclude the mean GPA of traditional, transfer, and non-traditional students in the junior year is not the same. Again, I'll notice this test doesn't tell us which group is different from the rest, or possibly all three groups are different from each other. It just tells us that they're not all the same. So that's the ANOVA. It's another use of the F distribution. There's actually several types of ANOVA. This is the most basic that we're going to look at in this course, and you can see more ANOVAs in more advanced statistics courses. But for now, we're comparing, do multiple groups have the same mean? We plug it into our calculator, we get an F statistic and a p-value, and we should be able to conclude, do they all have the same mean? Or is there a difference somewhere in the group? Try a few of these on the homework. We'll talk about it more in class, and we will see you then. This video is going to look at the important concept of finding a relationship between variables with what we call correlation and regression. So that's where our question stems from. Our question is, how do we test for a relationship between variables? And the first thing we're going to start with is just getting a visual of how the two variables are related using what is called a scatter plot. A scatter plot is basically just a graph of all of our data. So it's best illustrated with an example. Let's say a researcher collects a sample of the number of pages a person reads based on their age. So we've got, let's call the first column their age, and the second column the pages that they read. So we've got a 14-year-old who read 40 pages. There's a 21-year-old who read 45 pages. They asked a 33-year-old who read 92 pages. They asked a 45-year-old who read 167 pages. And they asked a 63-year-old who read 171 pages. The idea of a scatter plot is if we call the first column the independent variable x, and the thing that we think changes based on the independent variable, or the dependent variable y, we should be able to graph these to get a visual of how they relate to each other. Let's go up by tens on the x-axis. 10, 20, 30, 40, 50, 60, 70 years. And on the y-axis, we'll go up by 30s. 30, 60, 90, 120, 150, 180. And so we'll make a point for each one of these, and this is going to be what becomes our scatter plot. So at 14 years old, we'll go up to 40 pages, which is right about where that blue dot is. Then we've got a 21-year-old who goes 45 pages, so maybe a little bit higher. Then there's a 33-year-old who's going to go up to 92 pages. A 45-year-old who will go up to 167 pages. And a 63-year-old who will go up to 171 pages. And so we kind of can see a relationship here. But before we get into that, let's make sure our scatter plot is complete, because a good scatter plot will have titles and labels. So the bottom represents the age. Going up represents the pages. And we might say pages read by age for the title. And what we can see is the dots aren't exactly in a straight line, but they do kind of trend upwards. It seems that as age goes up, the number of pages goes up. And so we've got this relationship starting to establish visually. Now, our calculators can also make these scatter plots. So I want to show you how to make this exact same scatter plot on the calculator. So first, I'll write out the instructions. Then we'll go ahead and do it. First, we have to enter the data. And the way we enter the data is you'll start by hitting the Stat button, and then you'll select Edit. And then you can put X in list 1 and Y in list 2. Once you've entered the data, you're ready to make the graph. And the way we make the graph is first you'll have to hit the second button, and then you'll have to hit the y equals button, because above y equals, the second feature is stat plot. It's for graphing statistics. And you're going to go into the first stat plot and make sure it is on. Make sure you select the scatter plot, which is going to be the dots. And then you want to select what list you want, L1 and L2. Once you're done with setting up the stat plot, you'll hit the zoom button. And you'll select zoom stat, which will center you right on the statistics. So let's look at doing that on our calculator. First, we have to enter in our data. To do that, we'll start by hitting the Stat button, selecting Edit. And there's already stuff in these lists. To clear it out, I'll highlight the list name and hit Clear Enter, and that clears out the list. Clear Enter. And then I'll put in L1 my x's. My x's were 14, 21, 33, 45, and 63. And then L2, I'll put my y's, 40, 45, 92, 167, and 171. Now that I've entered in the data, to set up the graph, we'll hit Second and the Stat Plot button, which is the y equals button. Option number 1, we're going to make our scatter plot. First, you want to make sure you've turned it on by selecting On. There's lots of graphs. You want to make sure the dotted one, which stands for the scatter plot, is selected. And then L1 and L2 are my list. We're ready to see it. We'll hit the Zoom button. And near the bottom, maybe not the bottom, there it is. Number 9 on my calculator is Zoom Stat. What that does is that centers my graph around my statistics. And you see we end up with much the same graph we had before. The two dots next to each other, a dot, a high dot, and then another dot over to the side. And so now we've got our scatter plot on our calculator. But sometimes we're interested in more than just the dots. What we might be interested in is, can we draw a line that kind of models through the center of the data a best fit close to the dots? That is what we call our regression equation. So let's take a look at the regression equation, also known as the line of best fit, also known as the least squares line. Basically, a line that models those dots as close as possible. Well, since it's a line, we know the equation of the line is going to be y equals some y-intercept plus the slope times x. And in linear regression, we call that y equals a plus bx. A little different than algebra, where you probably learned y equals mx plus b. Similar setup, but now we use a for the y-intercept and b for the slope. The equations for a and b are quite complex, so we're going to have the calculator do our work for us to calculate the equation. And the way the calculator can do that is we actually run what's called the linear regression t-test. So we'll hit Stat. We'll scroll over to Tests. And we'll scroll down to the lin reg t-test. We can also graph it on our scatter plot graph by hitting the y equals button and then typing in the equation. So let's do that for our age versus pages example. So pulling back up my calculator, we're going to hit the Stat button, scroll over to Test, and near the bottom, you will see lin reg t test. Make sure you do linreg t-test, not any of the other linreg stuff. Linreg t-test. And hit enter. L1 and L2 are x and y. We're going to always select the not equals to button for our linreg t-test. And then if we hit calculate, it gives us a lot of information. We're going to come back to some of this information in just a minute. But specifically what we're interested in right now, if I scroll down, we see A is negative 5.523, and B is 3.083. I'm going to go ahead and round those to 2 decimal digits. So A is equal to negative 5.52, and B is equal to 3.08. Which means if I put that into my equation, y equals A, which is negative 5.52, plus B, 3.08 times x. This equation models as close as possible my scatter plot. If I hit y equals, I can type that in. Negative 5.52 plus 3.08x. The x button's right next to the stat button. And when I hit the graph button, what I'll see is I have a line that goes right through the middle of my dots. Seems to model that quite well. We have a line of best fit. The nice part about the line of best fit is I can use it to estimate values I don't have. Let's estimate the number of pages read by a 30-year-old. If we go back to the original data, we don't have 30 in here. But age is my x value. So if I plug in the age for x, we should be able to get a good estimate for what that 30-year-old is reading. So y equals negative 5.52 plus 3.08x. X is the age, my 30-year-old. And when I put that into my calculator, I end up with 86.88 pages. So round that maybe to 87 pages, we would expect this 30-year-old to read. One important thing to note about using the regression equation to estimate points is it only works within the domain of the problem. It only works between the high and low values. We can't estimate values outside of that range. So for example, this would be bad. Could we figure out a 3-year-old? Well, mathematically, it would make sense if 3 is the age. We'll just plug 3 in for the x, and we get negative 5.52 plus 3.08 times our 3-year-old. And that's going to equal to 3.72. So do we conclude that a 3-year-old is reading 3.72 pages? Probably not. There's not a lot of 3-year-olds that can read anything. Maybe their name. The problem is the 3-year-old is outside of our data. Our data had a low of 14 and a high of 63. We're only going to estimate values between those numbers. If we go outside of the data, the model can very easily break down. And so we want to be careful not to take the model further than it's designed to go. All right, I want to look at one more thing with regression and correlation, and that's what we call the correlation coefficient. And this is where the hypothesis test comes in, though we won't do it nearly as formally as we have in other contexts. The idea of the correlation coefficient is I have this red line on my graph that goes kind of through the blue dots, but not perfect. Well, how good of a model is that line of best fit? Is it close? Is it far off? What can we know from that line? This is what the correlation coefficient measures. And we have a special variable r that we use for the correlation coefficient. And it tells us two things about the graph. It tells us the strength and direction. First, r is between -1 and +1. We say if r equals 0, that tells us that there is no relation. No relation between the x and the y. The dots are completely random. And our line of best fit just has to go straight through the middle, but that doesn't even model it well. There's no relationship. Everything's random. If r equals +1, what that means is we have a perfect positive relation. Positive means we're going uphill. So now we're going to have these dots going uphill, and the line goes right through all the dots, uphill perfectly. That would make r equal to 1. Similarly, r equals to -1 means we have a perfect negative relation. Or we're going downhill. So now there's a bunch of dots going downhill, and the line goes right through the middle of all the dots going downhill. Now, there's no such thing as perfect data, so r very rarely is 0, 1, or -1. Usually it's somewhere in between. R might be -0.78, or r might be +0.23. And the closer it is to 0, the less relationship we have. And the closer to 1, the more likely we have a relationship. And the way we determine if there's a relationship is we do a t-test. It's called the lin-reg t-test, linear regression t-test, which gives a p-value that tells if the relationship between the two variables is significant. A p-value less than alpha of 0.05 will mean that we have a significant relationship. But r works hand in hand with this p-value because r tells the strength of the relationship. R could be positive or negative, but what we'll say is if it's between 0 and 0.1999999, the strength is considered to be very weak. There might be a relationship because the p-value tells us it's significant, but it's very weak, below 0.1999999. From 0.2 to 0.3999999, we say it's just a weak relationship. 0.4 to 0.59999 is a moderate relationship. But we like to see r bigger than 0.6. 0.6 to 0.7999 means we have a strong relationship. And on occasion, we end up between 0.8 and 1.0, which would be a very strong relationship. In addition to r telling us the strength of the relationship, and p telling us whether or not the relationship is significant, there's a third variable that we look at in analyzing correlation and regression, and that is r squared, which we get by squaring the r value. R squared tells the amount of variance. Actually, not variance, we'll say variation. In the dependent variable. That is explained by the independent variable. How much of the changes in that dependent variable are explained by changes in the independent variable versus other factors? This whole concept of the correlation coefficient is probably best seen by going back to our example. So let's go back to our age versus pages example. We can run the ln reg t-test on our calculator to find these important values, the t value, the r, the p value, and the r squared. So going back to our calculator, let's run it one more time. I'll hit stat over to test, and I'm going to do the ln reg t-test. My numbers are all already in there. So when I hit calculate, we see our test statistic, the t, is 5.09. We see that gives us a p-value of 0.0146. And if I scroll down, we will see an r value. R is 0.9466. And r squared is 0.896. Let me transfer all those values over here, and we'll talk about what they mean. So we had a t value of 5.09 when we round it, which resulted in a p value of 0.0147. Also, there was an r, our correlation coefficient, of 0.947. And r squared, it says, was 0.896. With linear regression, the null hypothesis is always that the relationship, which we represent with the Greek letter rho, looks like a p, equals 0. That means there's no relationship. The alternative is that rho is not equal to 0, or that there is a relationship. And we can see in our case, we're going to make a decision, because the p-value is less than 0.05, to reject the null and make a conclusion that there is significant evidence to conclude the alternative hypothesis, which says there is a relationship. There is a relationship between age and pages read. But we can expand on that conclusion a bit and say, because r is equal to 0.947, which if we scroll up in our notes, we see that puts us in the very strong category between 0.8 and 1.0. We can say the relationship is very strong. We can even go one step further and say, because r squared equals 0.896, we can claim that 89.6% of the variation in the dependent variable, or in pages read, is explained by the independent variable, or by age. And so you see, we don't end up with the traditional hypothesis test going through all the same exact steps we have before, but the pieces are still there, that we decided based on our p-value that there is a significant relationship. Based on our r, we can determine how strong the relationship is. And based on our r squared, we can say what percent of the variation is explained by the independent variable. So that's what we're looking at today, determining, is there a relationship? If there is a relationship, what that relationship is based on the equation y equals a plus bx, and also drawing the scatter plot so we can get a visual to see that relationship. We'll look forward to seeing you in class so we can look at these scatter plots, linear regression, and correlation a bit further.